So let's take a look at some summation rules. The first one deals with summing constants. So here my xi is some constant. Here I have 10 variables, x1 goes from 1 to 10, and each xi is a constant, in this case 6. If I sum these numbers, I will get 6 times 10, and the sum is equal to 60. What we saw in Excel was this expression. I summed I from 1 to 10, and I summed the number 6, and the result was 10 times 6. In general, if I have a sum which goes from 1 to an arbitrary n being any integer, and I sum an arbitrary constant, c can be 6 or any other number, then I will have precisely n variables, each one being equal to c, so the sum must be n times c. The proof of this is simply by the definition of multiplication. So sum I go from 1 to n of c is by definition c plus c plus c plus all the way to c, and I will have exactly n such c's. So that is by definition of multiplication n times c. In the same way, if I let the sum start at some other number such as m, and I go all the way to n, and I sum a constant, then I will have n minus m plus 1 terms here, because it starts at m, next one is m plus 1, goes all the way to n, in total n minus m plus 1, and that should be multiplied by c. So this is the first rule using summation sign. For the second rule, let's take a look at these 10 variables again, x1 through x10, and the sum of these xi is equal to 24. So here I create 3 times x1, 3 times x2, all the way down to 3 times x10. I multiply each x variable by the same number. So let's write here 3 times b1, 3 times 2 is 6, and we copy this down like this. Let's examine the sum of these new variables. We find that the sum is 72, which is precisely 3 times as large as 24. So the lesson here is as follows. If you sum a bunch of x variables and you get a number, if you then multiply each x variable by a constant, like here 3, then its sum will be 3 times as large as the original sum. Using mathematical symbols, what we just did was summation I goes from 1 to 10 of 3 times xi. And we said that was precisely 3 times as large as the sum where I goes from 1 to 10 of xi. So the general result here is that sum I goes from 1 to an arbitrary n. Doesn't matter if we had picked 12 or 15 in this example. And a constant times xi. It doesn't matter if we had picked 3 or any other number. Doesn't have to be an integer. Then that is equal to c times summation I goes from 1 to n of xi. We say that constants go outside the summation sign. So if I have a sum like this, c xi, I go from 1 to n, we take this constant and we move it outside the summation sign, and we write that as c summation I goes from 1 to n xi. The proof of this result follows from the distributive law. So if you remember the distributive law, we typically write it like this: A times a parenthesis of the sum of B and C is equal to A times B plus A times C. If you look at the expression to the right in the formula, it says C times summation I goes from 1 to n of xi. Well, that's the same thing as C times x1 plus x2 plus all the way to xn. The distributive law works equally well if you have more elements in the sum here. Here I have just 2 in the above formula, B and C. Here I have n terms. But the distributive law works just as well and says that this is C times x1 plus C times x2 plus all the way C times xn. Well, if I write that using summation sign, that is exactly sum I go from 1 to n C times xi. For the third example, I have 10 x variables, the sum of these, and I have 10 y variables, and the sum of the y variables is 15. Now what I want to do is create a new sequence of variables xi plus yi. So what I want to do is simply sum x1 and y1 here. So I write equal v1 plus e1. The sum of x1 and y1 is minus 5.1. I copy this down like this, and I have 10 new variables like this, and I can find the sum of these new numbers. The answer is 39, and that's precisely what you get if you add these two sums together. So what we just saw in the Excel sheet was that if I sum, I go from 1 to n, xi plus yi, that was the sum we had on the right, then that's equal to the sum I go from 1 to n of xi by itself plus the sum I go from 1 to n of yi. The proof of this result follows from the commutative and associative properties of addition. If you look at the sum on the left hand side, it says x1 plus y1 plus x2 plus y2 plus all the way to xn plus yn. While on the right hand side you have x1 plus x2 plus all the way to xn, and to that we add y1 plus y2 plus all the way to yn. And these two are equal simply because it doesn't matter in which order you add these numbers. In the sum to the left, I can just rearrange and add all the x's to each other first. Then I get this sum. And then I can add all the y's, and that gives me this sum. So these two sums must be the same. For the fourth rule, let's again look at 10 variables x1 through xn whose sum is 24. Let's divide these 10 variables into two parts. Let's say the first 6 variable, that's one part, and the last 4 is the second part. And let's take the sum of the variables in each part. Here I'll do the sum of the x variable in the first part. That gives me 12. And here I do the sum of the x variables in the second part. That gives me 12 as well. And if I add 12 to 12, I will get the total sum. So what we just saw was that if I do sum I goes from 1 to 6 of xi, and to that I add sum I goes from 7 to 10 of xi. That's exactly the same as sum I goes from 1 to 10 of xi. Or in general, what this says is that we can break up the sum any way we like. So the sum I goes from 1 to n of xi can be written as sum I goes from 1 to m, where m now is any number in between 1 and n, xi, plus sum where I goes from m plus 1 to n of xi. And the proof is quite simple. The sum on the left hand side is x1 plus x2 plus to xn. The sum on the right hand side is x1 plus x2 plus to xm. And to that we should add xm plus 1 plus all the way to xn, and these two sums are the same.